Good afternoon. Yeah, you're still awake after lunch. Very good. My name is Alan Price. I'm director of the John F. Kennedy Presidential Library and Museum. And along with my colleague, Stephen Rothstein, who's director of the John F. Kennedy Library Foundation, and all of the foundation and library staff, we welcome you to the JFK Space Fest programming today. We are grateful to Raytheon Company for its lead sponsorship of today's events and programs, as well as the Boeing Company and Vertex Pharmaceuticals. Thanks also to our underwriters of the Kennedy Library Forums, lead sponsors Bank of America, the Lowell Institute, and Gourmet Catering, and our media sponsors, the Boston Globe, Xfinity, and WBUR. I will put in a plug that if you like the programming that's going on today, and you're not currently a member of the library, that could be arranged. And so you could do that either at the bookstore or at the front desk where you entered. We'd love to have you in the family more officially. And I'm now delighted to introduce our first speaker for the afternoon. Su Curley is a senior engineer at NASA's Johnson Space Center, who has worked for more than 25 years on designing, building, and testing electric power systems for space flight vehicle applications and life support systems for spacecraft and spacesuits. She's currently working on engineering for crew survival spacesuits and hardware for the Orion Program, including the journey to Mars. Sue has kindly agreed to answer questions following her presentation. Please help me welcome Su Curley. It's great to see the kids up here.
Hi, everyone. Is this on? Okay. Hi. How amazing is this? First of all, I have to say, I have a little starstruck. I've been working at NASA for about 27 years, and so you would think that it's just become old hat. But our previous presenter, Dan Burbank, is a personal hero of mine. He spoke a bit about his expedition missions with he and Don Pettit, and it just so happens that for his expedition, I had some life support hardware flying aboard the space station that needed to be installed. It happens to be the CO2 scrubbing hardware that will be used for Orion, so it had a lot of big deal implications if it didn't work. And we had a unique situation where we had to fly part of it before finished building the rest of it. So the first time it was assembled was on orbit, which is not optimal at all. And so Dan was the first one to put his hands on the hardware. And then Don, and then Joe Acaba, and a couple more people before we finally got it working. But they cracked the box open, they got it put together, and then did the troubleshooting. So they're on, he's one of my all-time favorite heroes. So I'm a little bit in awe of following him up. I hope I can live up to that. But here we are on the golden anniversary of Apollo, right? Amazing. 50 years ago, people set foot on the moon. And I don't know about you, I'm from Houston, and the skies have been perfectly clear, and I thought it very poetic that it was a full moon this week. And I've stared at that moon every single night of this mission so far, and just imagining what it would be like to have taken that flight, to have gotten there, and then to be the guy who opens the door and steps out on the planet. Now, we had a journey up till then with Mercury and Gemini and some of our other stuff, and spacesuits have been an integral part of that. And I'm going to talk to you about the spacesuits back then and the spacesuits now, but not all of them. Frankly, I could tell you about all of them, but you don't have the time and I don't have the time today. So we're going to focus on our spacewalking hardware. I'm going to talk a little bit about the Apollo, what they used to step on the moon, and then this is my friend Larry. Larry and I travel around the country talking actual spacesuit. Well, parts of an actual spacesuit. It never flew like this. It flew in bits and pieces. And then after a while, materials out in space get worn out, kind of like the knees on your jeans for the kids in the office and the audience and the big kids in the audience, right? And you can't, it's not safe. So we bring them back to Earth and we use them for training, like Dr. Burbank said in the NBL, or we use them and bring them for space presentations and things like that, or we use them around the office to test a little bit and train a little bit and that night. And at the end of his address, he thanked all of the people that helped make that mission happen. And he specifically called out all of the spacecraft on the moon. And people don't think of it that way, but a spacesuit is actually a space. You're going to have problems getting tired, right? Less oxygen, the air is thinner, you're not doing as well of an oxygen exchange. You might need supplemental oxygen if you go any higher. 60,000 feet, 70,000 feet, you'll cross Armstrong's line, and the liquids in your body will boil. And above that, you need pressure suits. So none of today could open up the door and step outside on another planet. You need to have a spacesuit. And the spacesuit has to do everything a spacecraft does, and you have to walk in it. It has to fit you, and you have to walk in it. So the things about space that are hard are pressure, the vacuum of space. What will happen to you if you were to step out into the vacuum of space? So if you think of it like a balloon, right, as you go into lower pressure, the gas in the balloon expands. Well, that's what will happen to your internals. You have lots of gas inside. The air bubbles will expand. And what those will do is not exactly explode, because it's not an internal thing. You'll pop, so to speak, in those parts. Lots of other things will happen to you too, but that's just one of the things that happens if you should go out into vacuum. The second thing is there's no oxygen. You need a certain amount of oxygen to be able to breathe, to function, for your cells to function. That's why going up to high altitudes can be problematic. The thinner the air, even though the partial pressure of oxygen is the same, it doesn't exchange as much. If you are on the sun side of the space station, the temperature can be plus 250 degrees. If you're on the shady side, it can be minus 250 degrees. And that can all happen in the same distance that I just moved. So your spacesuit has to be able to handle a 500-degree temperature swing and not change the conditions inside for you. I don't know about you guys. I'm sorry, I'm from Houston. I may have brought this with me, but it's hot today, isn't it? Do you feel like being outside doing much? No, I don't really either. I have to walk back to my hotel later. Not really excited about that. And so you become less optimal the hotter it gets or the colder it gets. And we have to keep the internals to a suit in a nice working condition so that you will perform optimally. It's expensive to set you outside. It's hazardous to your health, so we need to maximize what you do while you're out there. Now, there's a couple other things. We don't have to worry so much about planetary problems. We'll talk about that in a moment. But micrometeors, Dr. Franklin Chang Diaz mentioned it earlier if you were able to catch his presentation. We have a lot of junk floating around in our atmosphere. And when you're out in space, if you're on the space station, for example, the space station's traveling at 17,500 miles an hour. And Dan Bernbeg showed you a picture hanging on the edge of it. How fast is he going? 17,005. What happens if he bumps into something the size of a pencil or a rock? That's going to have a very high impact. A car crash with a stationary body is less severe than if you're traveling and hit someone head on at high rate of speed, right? Because of the difference in speeds. And so you have to consider all of those things. The spacesuit has to be capable of protecting you should you encounter micrometeors. We have limitations, though. Materials are only so good. And you have to balance that against being able to wear it. So this particular suit can take a number 2 pencil diameter, 1/4-inch hole, right through it, and it'll give you 30 minutes to get back to the airlock on the space station, or if you're on a planet, to get back to your rover, to get back to your habitat. If you had supplemental oxygen on your rover, for example, then you'd get more time, because it's all about just feeding the leak then, right? Keeping the pressure inside this hole. If that earlier, what if you landed on a rock and you got a hole in your spacesuit? That'd be a really bad day, wouldn't it? Only briefly, but it'd be a bad day. And then I'll show you some video from the moon, and I want you to look at the condition of the suit. Larry he's been with me a lot, and he looks a little rough in my eyes because he's not pristine, but I want you to look at the condition of the Apollo suits when I show you the picture and just how much regolith is on them. Dr. Burbank talked about it. Everybody thinks it's like sand when you go to the beach. Well, in a way, because you never get it out of your car once you get it in, right? It never comes out. And that's what happens with the spacecraft. But unlike the beach, The regolith is charged, jagged particles. And so, like those natty little burrs that stick to you, if you think about that on a really tall or a really small scale, that's what's coating you everywhere. And so it's an irritant to you, it's an irritant to the suit, it's scratchy and it doesn't come off easily. And so you have to deal with that too. You can't easily just brush it off. So the spacesuit has to be able to handle all of that type of stuff and be wearable and be able to move around in it. So that's kind of why it looks like it does. Back in the Apollo days, we had successfully done Mercury and Gemini, and those were capsule-based space operations. You had basically a flight suit type of thing you wore to ride in the capsule. When we got to Gemini, we decided we wanted to go outside, right? See what happens. And so that suit had to be able to be pressurizable, but you're really just going to go out the door and kind of hang out and see, can you do it? Suit that provided the oxygen. Well, when we went to the moon, what's going to happen if you have a tether system? This contains everything you need to go on a spacewalk, 8.5 hours. It has all of your oxygen. It does your carbon dioxide scrubbing and a few other things. It has your water for cooling. It has your batteries and all the machinery to help make the suit work. And you carry it on your back like a backpack. And it's autonomous, so you're not connected to anything, right? So you can go over and you can pick up that rock if you want, and you can get into your rover and go wherever you want, up to the duration. I'd say only go halfway, so you can get back. But if you had charging stations at your rover, you could maybe go spend a week. If your rover's like that really cool NASA one, looks like a giant bubble with bug eyes, you could go hang out there, charge your suit up, get back in and do more EVAs, and be away from your vehicle for a while. And so Apollo was the first time we tested out that technology. The freedom that they had, the spacewalks were somewhere between 15 minutes and 7.5 hours in the spacesuit. 7.5 hours getting to explore the surface of the moon. Now, we talked a little bit about pressure. We're at sea level, and the atmosphere is pressing on our body. For the science geeky people, does anybody know what the pressure is in this room in pounds per square inch? 14.7, right? We're at sea level, 14.7. So it's pushing on you with that amount of air, which makes it, that's the way your body's used to. We're acclimated to that. When you go up into a plane, they acclimate the cabin, you know, and so you're at maybe 10.2-ish. That's why you have some pressure changes in your ear, but it's still comfortable enough for you to breathe. Start going up higher. The less air exchange, oxygen exchange you have in your lungs, the less efficient you are, and you'll stop functioning after time. But also, we talked about gas expansion. So your body gets edema. It starts to swell to fill the size of the container that you're in. Right now, that's your skin. Inside the spacesuit, it would be the volume of the spacesuit. So we have to keep some pressure on you to keep you in the shape of you and to keep you functioning well and breathing well. And that's in the range of 2.5 to 3 psi. So optimally, for going out on a spacewalk, you're inside a balloon. So think of yourself, if you can picture this, how many people play with balloon animals? How many people have ever played with balloon animals? How many people have kids who play with balloon animals? Oh, okay, now we got more hands. So think of yourself as being inside the balloon. You are a human balloon animal. And the thing that's protecting you is the balloon. What happens when he blows up the balloon? What does the balloon want to do? He wants to go straight, right? So how does he make the dog's legs bend? So he twists it, takes a little air out, right? Makes it squishier, twists it. So think of yourself inside the balloon animal. If we put 14.7 psi or even 10 in, what do you think you're going to look like? Now you see why they walk like that, right? So you have to trade it. Okay, I can go down to as little as 3 for a while. And so we like, you know, engineers, we like to have a little cushion just in case there's a bad day. So we ran the Apollo suit at 3.7. It was the minimal pressure we could do safely and still allow you to be able to move. And I'm going to show you a video in a couple minutes, and I want you to observe the movements. But if you see they look like the Michelin Man, this is why. Now that comes with a trade-off. What happens, are there any scuba divers? We're over here at the coast. Are there any scuba divers, recreational or otherwise? What happens when you come down from depth, which is high pressure, up towards the surface? What do you have to do? You have to take safety stops, right? Why is that? Decompression sickness. So you have nitrogen bubbles in your blood, right? And as you go to higher pressure, they get squished tiny, 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 and gas expands as you go to lower pressure. And if you make that rate too much, what happens? You get bubbles in your joints. You can get embolisms. So you control the rate at which those bubbles grow and allow your blood to soak that up. Think of that in the spacesuit. If we just drop you down to 3 and bring you back in and pressurize you, what's going to happen? You're at a risk of decompression sickness. So we do a couple things operationally in order to balance that. One of them is we do a pre-breathe of pure oxygen, because the spacesuit environment is pure oxygen. And so they spend time ahead of a spacewalk just breathing oxygen in order to flush as much of the nitrogen out of their system as possible. This helps reduce the possibility of decompression sickness. And then we slowly, just like your safety stops, bring the suit back up. I've watched or read The Martian. Or if you're a diver, it's really great for mobility, or mostly great for mobility, not so great on the human inside, right? Lots of time before, lots of time after, and the being able to change between inside your vehicle and into the spacesuit is not quick. And it's very fatiguing. If you did 4 scuba dives in one day, would you be all eager to go do 4 more the next day? Probably not. Maybe it depends on where you're diving. But so think of that relative to the space operations. We were learning all of these things. Now, Apollo used a one-suit solution. You can see, I've got a pointer, I should use it. You can see this suit right here. This is actually Neil Armstrong's suit, and all his suit hardware, not all of it, but most of it, laid out on the table right before his flight in this launch and entry suit. And so they put those on with the little bubble helmet up here in the corner, and you saw them walking out with their little portable air thing, go into their vehicle, right? If you look at the footage. So that was the suit they wore to get into the capsule for the dynamic phases. We call that the launch and entry or crew survival suit. But then it had to turn around and function as the EVA suit. Those are really 2 different things. The crew survival suit, you want something soft and comfortable for you to be, as Dan Burbank said, like pretty much scrunched up like this in your vehicle. And then what did he do? He landed like a dart in the ground, 20 G. If you had a 20 G impact, do you want hard stuff in your suit? No, because that's going to hurt you. So launch and entry suits need to be soft and comfortable. They're made for not having pressure. If they have pressure in it, it's a bad day. And so the EVA suit, on the other hand, needs to be pressurized. And then we talked about the balloon animal. If you're constantly out for 8 hours having to fight the arms and the legs of the suit, you're going to get pretty tired pretty quickly. In fact, the Apollo astronauts complained the most about the gloves. The glove technology here is far better than what it was for Apollo, but even so, it's not the best fatiguing thing that they had relative to the suit. And so, with all of that, you try to put in mobility like the suit so much. Right? All these hard metal joints, but that's not compatible with crew survival. The gloves, I'll show you with one of Larry's glove, has things in it to help bend the wrist and help make it more mobile so you don't have to fight the suit so much. Apollo didn't have these things. It was a one-suit solution. Now, they had some, you see kind of like this here, I think I have, yeah, and the sun visor, because that slipped over the bubble. So it was kind of a convertible solution. And that worked pretty well, but not perfect. So, you told me how to do this. Hang on. This is Charles
John, while you're
Duke.
sampling there, you might look around and see if you see any particular basalt.
The audio is less important, but he's going to try to take a core sample.
That's what I'm looking for. Good show.
Look at how dirty his
I
legs are.
told him you were. Well,
Uh-oh. Oh, man.
okay.
Think balloon animal.
We see that one went all the
Suit's
way
trying to
in.
keep it straight.
Not quite.
Okay, how do I stop? How do I stop
Hey, John,
that?
while
now?
you're sampling there, you might look around. Hey, John, while you're sampling
how
there,
to
you might
stop
look
it.
around.
Okay. So a couple of things to note. In the Apollo suit with the backpack, all of your weight is at the top, so your center of gravity is top and a bit aft, right? So your posture tends to be a little forward. Think a little bit like skiing, right? So you're a little bit leaned forward. And even though you weigh 1/6 as much on the surface, your inertial mass is the same. Once you get that baby in motion, it wants to keep in motion. There was a really cool spot in there, I don't know if you saw, there was about 2 seconds where he actually supported his entire body weight on the planet by his wrists. He had the perfect yoga pose going. And then he did push-ups and bounced himself back up on the planet. So that was kind of interesting, was it? That was part of a suit problem, and I'll talk about the problem in a minute. If we could switch, it didn't just happen when you fell down, but suit issues drove how they actually worked on the planet too. You're going to see how he moved to get around. Actually, this is he and Harrison Schmitt, the last two people on the moon. This is Gene Cernan and Harrison Schmitt. And they will be just going about getting to a work site.
I was strolling on the moon one day in a merry, merry month of December. Now, May, when much to my surprise, a pair of bunny eyes. Boy, is this a neat way to travel? Isn't it great? Jump-a-dum-dum-dum, jump-a-dum-dum-dum, jump-a-dum-dum-dum. I like to skip along, but me, boy, skip.
I have to admit that looks a lot like fun. And to be fair, I've flown on the Vomit Comet about 5 times, and I've done that, and that is very fun. But look at what they did. The last part, this part, we call that the kangaroo hop. Actually, he named that. And the other sort of interloping. Well, think of it in terms of the balloon animal. The soft goods want to stay straight. When you're walking naturally, you have a natural bend at your waist, but that suit was all a soft suit. So it didn't want to bend at the waist, and it didn't want to bend at the knees. And so they adapted to make the best of it and had some fun while doing it, but that's a suit problem, which is part of the reason, well, this is a microgravity suit, because Larry goes on ISS. And so Larry also has soft legs, but you'll notice he's got a waist ring. So he allows for natural movement here, which is vital if you fall down to be able to get up and help, right? And just do some of your more natural movements so you're not fighting the suit so much. Now, microgravity, you don't really need your legs. Everything's done. You do all your spacewalking at the space station level and microgravity with your hands. Your legs just kind of drag along for the fun of it. So think about launch weight, $20,000 a pound to send something to space. If you don't have to put metal in here and launch it, then you don't. You don't need it. He also has microgravity boots. Can he grip his with his hands? Hey, guess where the tread is? On his hands. So these were some things that we learned about planetary exploration relative to the guys on the moon. They were an excellent engineering study, and they provide a ton of humor. But if you're a medical sciences guy and you're watching that, oh my God, he's going to break a hip, twist an ankle. There's all kinds of physical things that could happen that'd be really bad. Now, fortunately, the moon boots, apparently with that structure, especially with the one inside the other, was very solid. They never felt like they were going to have any ankle problems. And so that they said, don't touch the boots. The boots are great. They're not quite like ski boots. They don't hold you in that tightly, but they really did restrict the ability for the ankle to shift around. That has its good and bad sides. When you walk, what are you doing? What if you wanted to climb up on a rock? Is it easier to do with your legs stuck in a position or to be able to move it around? So as we move towards planetary exploration, again, we're learning all the lessons from here, trying to take the good and the bad and to balance them. And we kind of did that relative to moving to our EVA suits. So this is Larry, and what you see here is Larry in his optimal EVA configuration. These are his sunglasses that help to reduce the glare. Now, much like you guys, if you're driving and it's about time for the sun to set or sun to rise. It's really hard to see sometimes. You put down the visor in the car, right? Larry has visors for that too. So all of Larry's work area in microgravity is right here in front of him. Everything that he does. So he can actually reduce the visibility, the reflection and the sunlight to optimize it for the work area right in front of them. And you can use it with the sun visor too, so it can get really dark. But that way it makes you more efficient, right? You saw, if you saw Dan Burbank's, excuse me, his videos, you saw one when he was getting suited up. There were big lights attached on here. They're basically mag lights. And so sometimes you go from light to dark. Transition's abrupt, but also it's dark over there. So you just press the button, you turn your lights on. They like to leave them on a lot too. But so this suit was modular to be able to help there. I showed you some of the mobility things that we've added. They're not in the legs in here because they're microgravity legs. So when we go to planetary suits, having bearings like this helps with movement in the hip, in the thigh, and in the ankle. But you have to contend with the regolith. Every time you break and make a seam, you can get that sand in the car that just doesn't go away in it. One of the things the Apollo astronauts talked about was the zipper in the suit. Because it's a launch and entry suit, you get into it like a onesie and you zip it up. Well, after the first EVA, it was already hard to work with. The regolith is so sharp and jagged that the teeth of the zipper were getting abraded, and now they have little bits of metal sticking out and makes it harder to unzip. What if you had to be a Mark Watley and go 3 or 4 times in a day? They weren't sure that they could use the suit after the 5 or 6 or 7 EVAs that they did. And so some of these things have to be a consideration in moving to a new suit solution. Now, Larry, when we transitioned from Apollo, which we knew who the crew was, it was a small crew size, it was certain crew size, their suits were semi-custom made, we transitioned into the era of the space shuttle. And when we did that, we were going to fly lots of people in a $10 million a piece range. We can't build one suit. Well, we never just built one suit. You had a flight suit, you had a backup flight suit, and you have a training suit, a system a lot like you're wearing today. The top part, what I call the shirt, comes in small, medium, large, and extra large. So do the pants. So if you have a bigger backside and a smaller waist or smaller shoulders, you can put on a small top and large legs. If you have broad shoulders and a narrow waist, you can kind of customize it, right? And then it can fit a variety of different people. It also uses the portable life support system. This is just kind of an upgraded version from what the Apollo had. Does a little bit different. We regenerate and use a CO2 scrubber that we take out of this when they come back from EVA, and we long process though, takes a little bit. So as we go forward, we have to think about engineering-wise, reducing the time for that, reducing the energy to use that high temperature microwave, right? Because if we're going to do 3 or 4 EVAs, we keep systems in your habitat to be able to clean all that. We need to be as efficient as possible. If you're 6 to 9 months away from Earth and you're doing all of that, you're going to run out of energy pretty quickly. Hard upper torso. And that's under here. I like to call it the armor because it protects all your vital parts, right? Your heart and your lungs and stuff. It also serves as the structure for everything else in the suit. The bliss mounts to it and all the other parts kind of hang from the hut. So it helps carry the weight some of the parts of the suit. Now, all of that's resting on you. So on the ground, this thing, fully loaded, if it had all of its controls and its backpack components, would be 313 pounds. Which, as you saw, if you saw Dan Burbank's pictures, they had a little stand that they got into to do NBL runs. They do everything assisted. If we do treadmill or other type things, we actually have a hook that we put on top and we hang you from the ceiling to carry some of that weight. It's still very heavy though, I have to admit. Still very heavy. In microgravity, it doesn't weigh anything. In fact, you float and center yourself inside the suit. So it's not really making any contact points too much. And so that's the main part of the suit. I'll talk about the rest of the parts of the suit here in pieces, because the astronauts, the Apollo astronauts talked a lot about the regolith. And after doing a couple EVAs on and off, I feel like I'm getting louder. These are comfort gloves. It's just real soft cotton, kind of like pajamas. And they help do a couple things. If you wear the comfort gloves, what happens when you work really hard? You start to sweat, right? These help wick the sweat off. Have you ever been swimming or in a bathtub or in a hot tub for a long time? What happens to your nails? They get really soft. What if you're doing hard working stuff and you have the crease of a glove going across what's becoming a softer and softer nail? You could lose a nail after your EVA. You could cause a blood bruise, I couldn't think of the word, on your nail bed. You're not likely to go out and do another one soon, right? You've got to recover. That's trauma. We have a lot of trauma with nails on our suits. And so comfort gloves help that a little bit by helping to wick away the sweat. On a planetary surface, they also helped. For the astronauts who did not wear the comfort gloves, some of that bleeding in the suit. So having something as simple as a cotton barrier in between you is almost a must-have. Those were preference items. They get to choose. But this was the first layer. Now, the astronauts also had that same thing in a pair of what we call thermal comfort garments, which is just a pair of long johns made of the same material for the sweat wicking purposes and comfort, so you're not sticking to it. Because this is the next layer of the suit. Looks kind of like a kitchen glove that you do dishes with, right? It's made kind of out of the same type of stuff. And when you're in it and sweating, it feels just like that. This is the balloon in our balloon animal. Just this. This is all that keeps you from death. That's it. And this little balloon is in multiple sections throughout the entire part of the suit. You can see part of it here. That is the balloon animal body. This is our pressure layer. Now, what happens to a balloon if you blow it too much? It pops. That would be a bad day. And we don't want that to happen. So this is conveniently called the restraint layer because it keeps your balloon from getting too big. It keeps you in a human-y shape, right? This goes over top this layer. And this is special. The microgravity glove is special, and I'll explain that in a second. But this restrains, and it's in all the portions of the suit as well to help keep the balloon contained so you can't overpressurize it and pop it. The glove is special. Remember, in microgravity, you do everything with your hands. We talked about the balloon animal and how hard it is. And these aren't custom made, so they don't work perfectly. And you're floating around in the middle of it. And if your elbow doesn't quite bend where the suit elbow bends, it can as best as we can with your hands. And so that's why this guy looks extra special. He has little tiny shoelaces on here to tighten it down as best as you can against your fingers to give you as much dexterity as possible. Now, something you guys can do at home just to get a feel for what it's like, go put on a giant oven mitt or a fire. The better you can make it, the more closely to your body, the more tactile sensations you're going to get from it. And so we do that with the restraint layer. Then the rest of the suit is all covered with this. This is what you see of him. This is our thermal micrometeor garment, TMG. NASA loves acronyms. And so this does exactly what it says. It protects against that 500-degree swing in the case of station, right? It also helps with the micrometeor impact, so it helps with the abrasions. Okay, and the regolith and all of that type of stuff, right, to protect the bladder layer from getting a hole in it. Now, when you're inside, you're sweating a lot. And so just like the Apollo guys, you have one of these. This is a liquid cooling garment. I think I messed my mic up. There we go. This liquid cooling garment goes on top of your thermal comfort units, underneath all of this, and it has tiny little tubes that run up and through it, right? And these tiny little tubes connect to this backpack, and they flow cold water through. And they cool you off. They help reject the heat into the backpack. And like the air conditioning in your car, you can choose to be less cool or a lot cool. You can't turn it off. The water has to flow, but you can choose. So this helps with thermal. And it's a full body solution for EVA because you can sweat in some crazy parts. We also have the ComCap. The ComCap looks just like what Neil had back in the day. Right now, keep it simple principle. Redundant earphones and microphones, they work really well. They're very reliable. But the Apollo astronauts, in talking with all of them after their missions, they had some really clever, these are really, really smart guys, and they had some clever ideas. We have, in the microgravity suit, we have this controller in the front, your display and control unit. It functions a lot like the dashboard on your car. You can see how much gas you have, you can see your tire pressure, you know. Basically, it tells you about all the suit systems, battery, oxygen, how your carbon dioxide, your fan speeds. You can talk to your buddies, you can turn up the volume on your CCA, those kind of. Get something on the ground, guess what? That box is now in your way, so you can't see your feet at all. In microgravity, you don't need to, but that's not a planetary solution. Even though it helps counterbalance the weight of the stuff in the back, you need to be able to see, so if you're less likely to trip and fall down. And so the Apollo astronauts suggested a heads-up display. That would be novel. Let's be Iron Man, right? Broadcast it right onto your thing. You can see your suit stuff. Projecting onto a sphere like this is not so easy. And it's 100% oxygen inside. Having electronic devices in there is not real great either. So all of these things are technical challenges. Oh, that's me. As we go to the moon. As we go to a planet. I have one more slide. So unfortunately, we're right in the middle of development. We're both in the middle of development. I work on the crew survival suit. There's my orange shoes because I work on the orange suit. That's the suit that they will wear on Orion to go to Gateway. You need a planetary suit, something that has what's necessary to make it feasible for people to do the work most efficiently. And because we're in development, I don't really have new pictures. I can suit. It's on a stand because it weighs a lot, but it has a rear entry. So this guy, to get in him, you have to slide in your pants. Pants on. Okay, I got my pants on. Okay. He hangs on the wall because he's got that big hut in the place. And you climb up from the bottom. And you climb in, you find the shoulder holes. Oh my gosh. Oh, okay. I'm ready to go for a spacewalk. Not really. So you have to have a buddy, tight your pants on, put your gloves on, put your helmet on. There's videos of how to get dressed as an astronaut on YouTube. I highly suggest reaching. That's a two-person job, and you can't do multiples of those very easily. So the new suit, you would walk this bad boy up to the wall and dock the back, and then the plis swings open like a door, and you can grab the bar on your vehicle and pull yourself out. Ready to go for an EVA, you grab that bar and you slide yourself back in, undock, it swings closed, and you're good to go. So these are things to help get you more like Mark Watley, right? To be able to do the things that we need to do on the planet. We learned a lot of these lessons from the guys who stepped on the moon 50 years ago. The physics hasn't changed, but the human understanding has changed, technology has changed, and we're trying to work hard. All the great things that they thought of back then to help them as they were the first people to try this stuff, we are working hard to incorporate and balance it against the engineering of reality and how things have to work. And so building on them is where we are today. And shortly, we're going to be back on the moon and on Mars. Thank you. I managed to keep it, I could talk forever. I managed to keep it in a reasonable time so I can take a few questions if anybody has questions out there. I can't really see you though. So, oh, there we go, that helps. I feel like a rock star, it's really weird. I'm just an engineer, so. Okay, wait, there's a microphone that'll help me. If you can go back to the microphone. Okay.
I can't read.
What you got for me?
What do you got?
What is it like to design a spacesuit?
That's a lot of, there's a lot to that answer. So we build a little and test a little. And I've talked about little it back 6 days. This, not going to work, right? So I get to play in the spacesuit a lot, and I study a lot, and I build a lot. And we do a little bit here and a little bit there. It's pretty cool, I won't lie. Oh, there's one over there. Yes, ma'am.
I'm curious if you had to think about suit redesign for women, because there were no women in the Apollo program, if that impacted how you changed suit design.
So, just like these videos show, I think you said, and let me recap, did we learn stuff from the Apollo program?
No, did you have to change the suit design because there were no women in the Apollo program? Did it make a difference?
Oh, so I'm not surprised I got this question. The anthro that we use to design suits are based upon about 40 or 50 different measurements. Now, granted, even the suit technology for this, the design was built in the 80s, right? So the demographic of what we were working with was different. We did have a small hut for this, not so much the Apollos were kind of custom suits. So yes, we have been working to better accommodate a smaller population, and part of that, if we can go back on the slide, so the biggest thing relative to smaller people, and I talked about the break where the suit breaks. If you're in a hut, for example, in this guy, you can see this is where the hard part stops. And if that hard part is here, you will never get your arms in here. So think of it relative to a small female in here, floating in the middle. You don't really get to position yourself, and now your suit is bumping here. So what we've done is the psi joint, and we've moved it way in, kind of like a wife beater t-shirt. And so that allows you to move your arms much more flexibly and accommodate a wider population size. Some of the competition has done things relative to narrowing down the waist of the suit, and that can work for you and against you. It limits the number of people you can get in if you try to make it tighter through this, which gives you a little bit more mobility, but then you can't put it on someone who has bigger hips. So there are some trade-offs, but we are actively working to accommodate more specifically a wider range of population. Good question. I'm sorry?
So when you're designing these suits, I know there's a large amount of stress that's placed on these when you're going on EVA. What kind of tolerance do you normally aim for when designing something that will walk either in microgravity or on a planetary surface?
So, and it depends on what part you're in. For example, the barrel part of the suit has the pressure is the stressor part. For the expansion against the seams and the joints. We tend to use either a 2 or 4 factor of safety, and so we'll test it if it's an 8 psi suit, which our new ones are working towards to help reduce EVA time and both in and out. That's a much higher pressure, but we'll test it to 15, 17, 20 to make sure that the garments can accommodate it, bolstering the seams and that type of stuff. Relative to abrasion, for example, on the ankle, that has a very different thing, right? So your treads and your harder materials are what are going to take the impact for those. So it's dependent on what part of the suit it is. Tolerances is kind of a sneaky thing because you're trying to keep dust out. So the smallest amount of holes you can make is the best you're going to do. Yes, sir.
How do they use the bathroom?
Say again?
How do they use the bathroom?
So, much like a car trip for adults, not so much for kids, if you're only going 4 or 5, 6 hours away, you might not stop, right? So in a spacewalk, currently, this is what you do. Anybody who's wearing a spacesuit has one of these on. I don't want to clean your suit when you get back if you're not wearing it. You have to clean it yourself. So every time you see someone in a suit, this is what they have on. Now, when we go into long duration contingency things where you might get stuck in your suit for a long time, like the Apollo guys used a urine device, which had a body interface and a tube, and it would pull urine away from the body and store it in a bag. Not really the most elegant, but if you're having a bad day, just getting the fluids away from your body is the big thing, right? No contact with the skin because you don't want to end up with sepsis over time and irritation. Get it out of the suit so you're not contaminating the environment you're in. So for a long stay in a suit, that's one thing. Unfortunately, solids is a much more challenging problem. We don't have an effective way to get those out of the suit at this point. The poor Apollo guys didn't even have a potty on their capsule, and so they used a bag. They hated the bag. And as humans do, if there's something you hate, you won't use it. So they did some things, if you study, they had some medicine that would constipate them. And so one poor sap took so much, he didn't go to the bathroom for 8 days, his entire 8-day mission. Now that can cause other problems, right? Health issues. So we don't want that either. We're working towards designing something that's can capture solids and not be absolutely horrible, because at the end, as long as we get you home alive in a bad day, like that's the goal, right? So for short duration stuff, 8, 10, 12 hours, the diaper is what we use. Yes?
How did you become interested in like making spacesuits?
I think the interest is probably always there, right? That's something that you have to find within yourself. But spacesuits are fascinating because they're an engineering marvel, they're a human medical science marvel, they're a computer electronics marvel. They have everything a spacecraft is in the same thing. So there's so much that you could find, like I like to build things with computers, or I like to play with Legos, or man, I really like materials. There are so many different things that you could find that you like that apply to spacesuit stuff. And if you're just digging the idea of putting on something like this and playing in it and having it go out into space, then it's really the place to be.
Hi. Right here.
Hi.
Hi. Thanks for a great speech, by the way. I really enjoyed your presentation. My question is around eating and drinking as we have longer duration EVAs. So as we're gloved and helmeted, there's no way to scratch your face or put
That's
food
right.
in your mouth. So is there any plans to introduce intake of food or anything like that as the duration of the spacewalk increases?
Yes, actually, so currently what we use, we don't feed you for 8 hours. We did try a snack bar, but remember the idea, like she said, is you can't reach in there to hold it. So imagine some semi-mushy thing on a stick next to your face. And you don't eat it all. And if it makes crumbs, So that didn't work so well, so we abandoned that. Right now they use a drink bag, and the drink bag mounts inside the hut, and the little straw, oops, sorry, I keep doing that. The little straw sticks up and they can sip. It's an astronaut sippy cup, holds 1.5 liters of water. We've tried sports drinks and stuff, but keep in mind, here's a logistics thing. If you're going to Mars and you pack something with sports drink in here, think about what happens to sugars as they sit for a while, right? So you might want it to be something that has kind of like a sodium stick, like your glow sticks, right? Maybe it's got the powder encapsulated, and when you go to use it, you break it, and then you mix it. It's water up until then. So some ideas in the works for that. That was one of the things the Apollo astronauts talked about. Now, they had an unfortunate thing. They had to put chlorine tablets in, and they didn't really have any way to mix it. So sometimes so there was an orange powder drink that they would use and mix it up there so it was orange tasting chlorine. But the concept is similar, right? In the new crew survival suit, that could be up to 6 days, we also have a drink port. So depending on how you make the interfacing bags, they could have a liquid type nutrient that's a food-like thing to help you with your caloric intake. But there's no way, unless you were to stick like gummy bears along the surface of the helmet or something, there's no way to really add food to it. Now, if you're stuck in a suit for 6 days, we're probably reducing your calories anyway, because we still have to deal with the post-processing of it.
Thank you.
Yes, ma'am.
Do they sleep in their spacesuit?
So in this case, no, because they only go out to do a task. Say if you guys are up here, it snows, you had to go out and shovel the driveway. You put all your snow pants on, your snowshoe, your snow jacket on, your hat and your gloves and everything, you go out and shovel the driveway. Well, you don't take a nap right there. Sometimes it feels like you should, but you don't. You come inside and take all of that off, and that's how a spacewalk works. We talked about the possibility of using a rover as your home away from home. So the idea is not to sleep in your spacewalking spacesuit. Now, relative to the crew survival suit in that 6-day contingency when you're away, or if you're going 6 to 9 months to Mars and there's something bad, and you need to be in it for an extended duration, then you might have to sleep in it. But keep in mind, in microgravity, you're the balloon inside the balloon. You're floating around inside of it, kind of like this. And it looks a lot like what Dan Burbank had with the posture you kind of get into, and you'll just eventually fall asleep in there. Yes, sir.
Has there ever been an issue where there has been like a hole in one of the suits?
We have not had one on orbit, and even with all the dynamics on the surface of the moon, we did not have a problem with a hole in the suit. We have had 2 ground-based issues. And so one of those happened with a glove abrasion, a glove hole, and one of them happened with a bearing area. And so as I talked about, what happens to the body when it becomes exposed to vacuum? It swells. And so the issue was discovered because the subject's body started swelling, but what happened is you swelled to the size of your container, so their body resealed at this part, at this joint, so only this was at vacuum, and all the rest of the suit managed to stay at pressure. So in test conditions, it's heavily monitored. Everybody's right there. We repressurized the chamber, got them out of the suit. The swelling went down as we repressurized, and there was no lasting damage. Okay, I think I have time for one more.
Do you wear normal clothes under it, and why?
No, you don't wear normal clothes under it for bulk purposes, and things like buttons and stuff would be an irritant. So you wear the soft cotton, like your soft cotton pajamas. No underwear though, because you got one of these on, and it's meant for reducing bulk and thermal protection and wicking away, just like you would wear a tank top under a shirt here when it's hot. In order to help pull the sweat away from your shirt, that's what you do underneath the suit, because the problem with the suit is heat, not cold. Thank you, sir.
And in the meantime, we invite you to try out some of today's special interactive presentations and hands-on activities that go from now until 4 o'clock, and to visit our museum galleries, which are open until 5 o'clock today. See you at 2:30.